Have you ever wondered what would happen if our planet just stopped, not gradually slowing down like a spinning top coming to rest, but suddenly completely ceasing its rotation? It's a question that sounds simple enough, but the answer reveals just how delicately balanced our world really is. Tonight, as you settle in for a peaceful journey through science, we're going to explore this fascinating thought experiment together. Before we begin, I'd love to know where in the world you're listening from tonight. Are you tucked into bed as the evening winds down? Or perhaps it's early morning where you are, and you're starting your day with some gentle curiosity. Wherever you are, whatever time it is, I'm glad you're here. If you enjoy these quiet explorations of science, please consider giving this video a like and subscribing to join our community of weary researchers. It helps more people find these peaceful moments of wonder. Now, I should mention that while this video is designed to help you drift off to sleep, there's always the small chance it might be just interesting enough to keep you awake. But if you do find yourself lying there at midnight, thinking about the physics of planetary rotation, well, at least you'll have learned something fascinating along the way. So close your eyes if you like, take a deep breath, and let's gently explore what would happen if Earth stopped spinning. Don't worry, our planet isn't going anywhere. This is just a peaceful thought experiment, told softly as we drift through the science together. The first thing to understand is just how fast our planet is actually moving. Right now, as you listen to this, you're spinning through space at approximately 1,000 miles per hour if you're near the equator. That's faster than most commercial aircraft fly. The exact speed depends on where you are on Earth's surface. At the equator, the land beneath your feet is racing along at about 674 kilometers per hour, while if you were standing at the North or South Pole, you'd barely be moving at all, just gently rotating in place once every 24 hours. This rotation is something Earth has been doing for over 4.5 billion years. It's not powered by an engine or motor. It's simply the leftover momentum from when our planet first formed. Picture the early solar system as a vast, swirling cloud of dust and gas. As gravity pulled this material together to form planets, that spinning motion was preserved. It's a bit like a figure skater pulling their arms in during a spin, except the skater is a planet, and the spin has been going on for longer than life has existed on Earth. The rotation gives us day and night, influences our weather patterns, and even affects the shape of our planet. Earth isn't perfectly round, it's slightly flattened at the poles and bulges at the equator, all because of this constant spinning. But what if, in some impossible scenario, it all just stopped? Let's imagine for a moment that some cosmic force could simply halt Earth's rotation instantly, like pressing a pause button on a spinning globe. The consequences would be immediate and, quite frankly, catastrophic beyond imagination. The first and most violent effect would come from something physicists call the conservation of angular momentum. This is one of the fundamental laws of physics, and it states that a spinning object will continue spinning unless acted upon by an outside force. If Earth suddenly stopped rotating, everything on its surface, including the atmosphere, the oceans, and yes, everything not firmly anchored to the bedrock, would continue moving at that original speed of roughly 1,000 miles per hour. Picture yourself standing in a field on a calm day. If Earth's rotation suddenly ceased, you wouldn't gently come to a stop. You'd be flung eastward at tremendous speed, along with every car, building, tree, and grain of sand around you. The atmosphere itself would become a hurricane of unimaginable proportions, with winds screaming across the surface at speeds that would make the strongest tornado look like a gentle breeze. But it gets worse. The oceans, no longer held in their current patterns by the planet's rotation, would begin to redistribute themselves. Currently, Earth's spin creates a centrifugal force that causes our planet to bulge slightly at the equator. This bulge is subtle, but it's enough to affect where the oceans settle. Without rotation, this bulge would disappear, and all that extra water would flow toward the poles, The result would be a complete reshaping of Earth's geography. Computer models suggest that the continents we know today would be partially submerged, while new land would emerge around the equator. What we currently call the Atlantic and Pacific Oceans might become two separate polar seas, with a ring of land circling the globe where the equator used to be underwater. Meanwhile, the sudden stop would trigger massive earthquakes as the Earth's crust adjusted to its new, non-rotating state. Tectonic plates would shift violently, mountains would crumble, and new ones might be born from the chaos. The very ground beneath our feet would become unstable, heaving and buckling as the planet's entire structure reorganized itself. But perhaps most ominously, Earth's magnetic field would begin to weaken and eventually disappear. Our planet's magnetosphere, the invisible shield that protects us from harmful solar radiation, is generated by the motion of molten iron in Earth's outer core. This motion is closely linked to the planet's rotation. Without it, the magnetic field would slowly fade, leaving Earth vulnerable to the constant stream of charged particles from the Sun. This loss of magnetic protection would have devastating effects on life. The solar wind would gradually strip away our atmosphere, much as it did to Mars billions of years ago. The ozone layer would be destroyed, allowing deadly ultraviolet radiation to reach the surface. Even if any life managed to survive the initial catastrophe, the long-term effects would make Earth uninhabitable. Now let's consider what would happen to day and night. Currently, Earth completes one rotation every 24 hours, giving us our familiar cycle of day and night. If the planet stopped spinning but continued to orbit the Sun, one side would face the Sun continuously, while the other remained in permanent darkness. A day would last an entire year, with 6 months of continuous sunlight, followed by 6 months of endless night. The temperature differences would be extreme. The sun-facing side would become a scorching desert, with temperatures potentially reaching hundreds of degrees Fahrenheit. Meanwhile, the dark side would freeze into a polar wasteland, with temperatures dropping far below anything we experience at Earth's poles today. The only potentially habitable zone would be a narrow twilight region between the two extremes, where the sun would hang forever on the horizon. These temperature differences would create massive atmospheric disturbances. The hot air on the day side would rise and flow toward the cold side, while the cold air would sink and flow back toward the day side. The result would be constant, violent winds circling the globe, creating permanent storms far more powerful than any hurricane we've ever seen. The effects on weather would be unlike anything in Earth's current climate. Instead of the complex, ever-changing weather patterns we know today, driven by the planet's rotation and the Coriolis effect, we'd have a much simpler but far more extreme system. Giant convection cells would form, with hot air rising on the day side and cold air sinking on the night side, creating a planetary-scale wind system of devastating power. Of course, none of this is actually going to happen. There's no known force in the universe that could suddenly stop Earth's rotation. Even the most catastrophic cosmic events, like asteroid impacts or nearby supernova, couldn't halt our planet's spin instantly. The amount of energy required would be incomprehensibly vast, far greater than anything we could imagine. Earth's rotation is gradually slowing down, but this is a natural process that takes place over millions of years. The gravitational pull of the moon creates tides in our oceans, and the friction from these tides slowly saps Earth's rotational energy. As a result, our days are getting longer, but only by about 1.7 milliseconds per century. At this rate, it would take hundreds of millions of years for Earth's rotation to slow significantly, and billions of years for it to stop completely. Even then, the process would be so gradual that life would have time to adapt. The gradual slowing would allow the atmosphere and oceans to adjust slowly, preventing the catastrophic redistribution of matter that would occur with a sudden stop. By the time Earth's rotation finally ceased, if it ever did, our planet might be a very different place, but the transition would be peaceful rather than violent. But let's return to our thought experiment for a moment. If somehow Earth did stop spinning, would there be any safe places? The short answer is no, not really. The initial catastrophe would be global and total. However, if we're imagining impossible scenarios, we might as well imagine impossible survival strategies. Underground bunkers might offer some protection from the initial chaos of flying debris and hurricane-force winds. Being far from the oceans might help avoid the massive tsunamis that would result from the sudden redistribution of water. But even in the most protected locations, survivors would face a world transformed beyond recognition, with no atmosphere to breathe, no magnetic field for protection, and no stable climate to support life. The more you think about this scenario, the more you realize how perfectly balanced our current world really is. Earth's rotation isn't just a curious fact about our planet, it's fundamental to everything that makes our world habitable. It drives our weather, shapes our geography, protects us from radiation, and gives us the familiar rhythm of day and night that all life on Earth has evolved around. In a way, contemplating what would happen if Earth stopped spinning makes us appreciate what we have. Every sunrise and sunset, every gentle breeze, every drop of rain is possible because our planet has been spinning faithfully for billions of years. The rotation that we never think about is actually one of the most important things happening around us every moment of every day. As you drift off to sleep tonight, you might find it oddly comforting to know that Earth will keep spinning, just as it has for eons before you were born, and will continue long after. The same rotation that brings the dawn each morning and pulls the stars across the night sky is also what makes our world a place where life can flourish, where oceans can exist and where we can lie safely in our beds, pondering the wonders of the cosmos. So rest easy, knowing that our planet's ancient spin continues its eternal dance, keeping us safe, keeping us stable, and keeping our world exactly the way it needs to be for life to exist. The Earth beneath you is moving at incredible speed through space, but it's a motion so smooth and constant that we never feel it. A cosmic rhythm that rocks us gently to sleep each night under the turning stars. Sweet dreams, fellow travellers on this spinning world of ours. Of course, the question that immediately comes to mind is, what would actually happen if Earth suddenly stopped spinning? And I do mean suddenly, not the gradual slowing we see in reality, but an instantaneous halt, as if someone flipped a cosmic switch and brought our planet's rotation to a complete standstill. The answer, I'm afraid, is nothing short of catastrophic. You see, everything on Earth's surface is currently moving eastward at roughly 1,000 miles per hour at the equator. That includes you, your house, the trees outside your window, every car on every highway, and every drop of water in every ocean. We don't feel this motion because we're all moving together, like passengers on a smoothly cruising airplane. But if Earth were to suddenly stop rotating while everything else continued moving at that tremendous speed, well, the results would be beyond devastating. Let's imagine that young man I mentioned earlier, driving leisurely on a sunny afternoon, perhaps passing a cluster of restaurants in the distance. If Earth suddenly ceased its spin, he would see himself, his car, the road beneath him, the vegetation around him, those distant restaurants, and everyone and everything inside them suddenly launch it into the air, hurtling eastward at over 1,000 miles per hour. The ground would stop, but everything on top of it would keep going, obeying Newton's first law of motion. An object in motion stays in motion unless acted upon by an external force. This wouldn't be a gentle tumble or a minor inconvenience. Cars would become projectiles. Buildings would see their foundations stop moving while everything above ground level continued eastward at supersonic speeds. Trees would be ripped from their roots, not just by wind, but by their own inertia. People would be flung through the air like leaves in a hurricane. The atmosphere itself would continue racing eastward, creating winds of unimaginable violence, atomizing the surface of bodies of water and creating tsunamis that would make any natural disaster in recorded history look gentle by comparison. But the immediate chaos of flying debris and hurricane-force winds would only be the beginning. The sudden stop would trigger massive earthquakes, as the Earth's crust, no longer spinning smoothly, would reel and buckle under the stress. These wouldn't be ordinary earthquakes. They would be unlike anything our planet has ever experienced, reshaping continents and triggering landslides on a scale that defies imagination. And then there are the oceans, those vast bodies of water suddenly freed from the rotational forces that have been shaping them for billions of years, would begin to redistribute themselves across the planet's surface. You see, Earth's rotation causes our planet to bulge slightly at the equator, about 21 kilometers more than at the poles. This bulge exists because of centrifugal force, the same force that pushes you against the door when your car takes a sharp turn. Without rotation, there would be no centrifugal force and no equatorial bulge. All that extra water currently held in place around the equator would go rushing back toward the poles. Computer models suggest that this would create a completely new geography, a supercontinent circling the equator like a giant belt, separating two massive polar oceans. Most of the land masses we know today would be underwater, submerged beneath hundreds of feet of displaced seawater. The ramifications would extend far beyond geography. Earth's magnetic field, which protects us from deadly solar radiation and cosmic rays, is generated by the motion of liquid metal in our planet's outer core. This motion is directly tied to Earth's rotation. Without that rotation, our magnetic field would begin to weaken and eventually disappear entirely, leaving Earth's surface exposed to radiation levels that would be lethal to most life forms. The very concept of day and night would be transformed beyond recognition. Instead of our familiar 24-hour cycle, we would experience 6 months of continuous daylight, followed by 6 months of total darkness. The side of Earth facing the sun would become a blazing furnace, with temperatures soaring to levels that would make the hottest deserts seem cool by comparison. Meanwhile, the dark side would become a frozen wasteland, colder than the most brutal Arctic winter. This dramatic temperature difference would create atmospheric chaos. Massive storms would rage at the boundary between the day and night sides, as superheated air from the light side collided with frigid air from the dark side. These wouldn't be ordinary storms. They would be perpetual tempests of unimaginable violence, with winds that would make hurricanes look like gentle breezes. The effects on life would be equally devastating. Plants on the dark side would die from lack of sunlight, while those on the light side would be scorched by the relentless heat. The delicate balance of ecosystems that has taken millions of years to develop would collapse within months. The food chain would crumble from the bottom up, starting with the plants and working its way through every level of life on Earth. Even if some pockets of life managed to survive in the narrow twilight zone between the day and night sides, they would face additional challenges. Without the stabilizing influence of rotation, Earth's weather patterns would become chaotic and unpredictable. The gentle cycles of evaporation and precipitation that water our crops and fill our rivers would be replaced by violent extremes. Perhaps most sobering of all is the realization that there would be no going back. Once Earth's rotation stopped, there would be no natural mechanism to restart it. The planet would be locked in this new hostile configuration for the remainder of its existence. Now, I should emphasize that this scenario is purely theoretical. The amount of energy required to stop Earth's rotation would be so enormous that there's no known force in the universe capable of doing it suddenly. Earth's rotation is slowing down naturally, but at such a gradual pace that it takes about 50,000 years for our day to lengthen by just 1 second. This gentle deceleration gives life on Earth plenty of time to adapt, and it will be billions of years before the effects become truly significant. But as a thought experiment, the sudden stopping of Earth's rotation serves as a powerful reminder of just how delicately balanced our planet's systems really are. The gentle spinning motion that we take for granted is actually one of the fundamental forces that makes Earth habitable. It shapes our weather, creates our magnetic shield, regulates our climate, and maintains the very rhythm of life itself. So the next time you watch a sunset, or feel a gentle breeze, or simply enjoy the regular cycle of day and night, take a moment to appreciate the quiet miracle of Earth's rotation. That steady, invisible spin isn't just moving us through space, it's creating the conditions that allow life as we know it to exist. In a universe full of hostile, barren worlds, our spinning planet is a rare oasis of stability and life, and that rotation is one of the key ingredients in the recipe that makes it all possible. Now that we've journeyed through the birth of galaxies and explored the fundamental forces that shaped our universe, let's turn our attention to something deeply personal, yet cosmically significant. Why does Earth have seasons? This gentle rhythm of change that governs our lives, from the first spring buds to the quiet hush of winter snow, isn't just a local phenomenon. It's the result of our planet's ancient dance with the sun, a celestial waltz that's been playing out for billions of years. Picture this. Earth is like a spinning top that's slightly tilted as it glides around the sun. This tilt, a modest 23.5 degrees from vertical, might seem insignificant, but it's the quiet architect of every season you've ever experienced. Without this tilt, our world would be a very different place, one of eternal sameness where the equator bakes in perpetual summer while the poles shiver in endless winter. The story begins about 4.5 billion years ago, when our young planet was still finding its footing in the cosmic neighbourhood. During those chaotic early days, a Mars-sized object called Theia collided with Earth in what scientists poetically call the giant impact hypothesis. This wasn't just any collision, it was the cosmic event that would forever change how we experience time and weather. The impact not only created our moon from the debris, but it also knocked Earth off its perfectly upright axis, giving our planet that crucial tilt that would become the heartbeat of seasonal change. Now, as Earth orbits the Sun once each year, this tilted axis means that different parts of our planet receive varying amounts of sunlight throughout the year. When the northern hemisphere tilts toward the Sun, it receives more direct sunlight and longer days, bringing the warmth and growth of summer. Meanwhile, the southern hemisphere tilts away, experiencing the shorter days and cooler temperatures of winter. 6 months later, the roles reverse, and what was once summer becomes winter, and winter becomes summer. But here's where it gets beautifully complex. The tilt doesn't just create a simple on-off switch between hot and cold. Instead, it orchestrates a gradual transition, a slow breathing of the planet that we experience as spring and autumn. During these transitional seasons, neither hemisphere is tilted significantly toward or away from the sun, creating those perfect moments of balance when day and night are nearly equal in length. Consider the spring equinox, that magical moment around March 20th, when winter's grip finally loosens and the world begins to wake up. On this day, the sun sits directly above Earth's equator, and every place on our planet experiences roughly 12 hours of daylight and 12 hours of darkness. It's a moment of cosmic equilibrium, a pause in the planetary dance before the northern hemisphere begins its tilt towards summer. The physics behind this seasonal symphony is elegantly simple, yet profound in its effects. As the northern hemisphere tilts toward the sun during summer, the sun's rays strike the surface more directly, concentrating their energy and warming the land and sea. The days grow longer too, giving the sun more time each day to heat the Earth's surface. This isn't just about temperature, it's about life itself responding to the rhythm of light and warmth. Plants have evolved exquisite sensitivity to these changes. The lengthening days of spring trigger a cascade of biological responses. Sap begins to flow in maple trees, Flower buds swell with anticipation, and countless seeds that have waited patiently through winter's dormancy suddenly spring to life. Animals, too, are choreographed by this celestial dance. Birds begin their epic migrations, following ancient routes encoded in their DNA, while bears emerge from hibernation and many species begin their mating rituals, timed perfectly to when food will be most abundant for their young. But Earth's tilt creates more than just seasonal changes. It creates the very possibility of complex life as we know it. Without this stabilizing tilt, maintained by our moon's gravitational influence, our planet's axis would wobble chaotically. The climate would be wildly unstable, swinging between extreme conditions that would make it nearly impossible for complex ecosystems to develop and thrive. Different parts of our planet experience seasons in wonderfully different ways. Near the equator, the seasonal changes are subtle, marked more by shifts in rainfall than temperature. Here, instead of 4 distinct seasons, there might be just 2, wet and dry. The sun never strays far from directly overhead, so the temperature remains relatively constant throughout the year. Travel toward the poles, however, and the seasonal differences become increasingly dramatic. In the Arctic and Antarctic regions, summer brings the midnight sun, where the sun never sets for weeks or even months. Conversely, winter brings polar night, a time of darkness that can last just as long. These extreme seasons shape everything from the behaviour of polar bears and penguins to the formation of sea ice that influences ocean currents around the globe. The timing of seasons is also beautifully reversed between the northern and southern hemispheres. When it's summer in New York, it's winter in Sydney. When cherry blossoms bloom in Japan, autumn leaves are falling in Argentina. This global dance means that somewhere on Earth it's always spring, always summer, always autumn, always winter. Our planet is simultaneously experiencing every season at once, a reminder of the beautiful diversity that our tilted world creates. Even the length of seasons varies in fascinating ways. Earth's orbit around the Sun isn't a perfect circle, but rather a slight ellipse. This means that our planet is sometimes closer to the Sun and sometimes farther away. When Earth is closest to the Sun, called perihelion, it happens to occur during the Northern Hemisphere's winter, around early January. You might think this would make winter warmer, but the effect is actually quite subtle compared to the influence of our planet's tilt. The distance variation does, however, make Northern Hemisphere winters slightly milder and summers slightly cooler than they would be in a perfectly circular orbit. This orbital dance has changed over time and will continue to change. The tilt of Earth's axis isn't constant. It varies between about 22.1 and 24.5 degrees over a cycle of roughly 41,000 years. When the tilt is greater, seasons are more extreme. When it's smaller, seasonal differences are more subtle. These variations, combined with changes in Earth's orbit, help drive long-term climate cycles, including ice ages. The seasonal cycle also drives one of the most important processes on our planet, the global circulation of air and water. As the Northern Hemisphere warms in spring and summer, it affects wind patterns, ocean currents, and the distribution of moisture in the atmosphere. The monsoons that bring life-giving rain to billions of people in Asia are fundamentally driven by seasonal heating differences between land and sea. The jet stream, that river of fast-moving air high in our atmosphere, shifts its position with the seasons, steering storm systems and influencing weather patterns across entire continents. Perhaps most remarkably, seasons have shaped human culture in profound ways. Our ancestors, intimately connected to the natural world, organised their lives around seasonal rhythms. They planted and harvested according to the seasons, celebrated festivals marking the solstices and equinoxes, and developed rich mythologies explaining the annual cycle of death and rebirth in nature. Even today, in our climate-controlled, artificially lit modern world, We still feel the pull of seasonal change in our biology and our emotions. Scientists have discovered that many humans experience seasonal changes in mood, energy levels, and even brain chemistry. The shorter days of winter can trigger seasonal affective disorder in some people, while the longer days of summer often bring increased energy and optimism. Our bodies still respond to the ancient rhythm of light and darkness, warmth and cold, growth and dormancy that has shaped life on Earth for millions of years. The beauty of seasons lies not just in their individual character, but in their endless cycle of change. Spring's promise of renewal, summer's abundance of life, autumn's graceful preparation for rest, and winter's quiet contemplation. Each season teaches us something different about time, change, and the natural world. They remind us that change is not something to fear, but something to celebrate, a fundamental part of the cosmic dance that makes our planet so uniquely beautiful. As you drift off to sleep tonight, perhaps you can imagine Earth on its tilted journey around the sun, carrying all of us through space on this slow, eternal dance of seasons. Somewhere on our planet, it's morning, and spring flowers are opening to the sun. Somewhere else, it's evening, and autumn leaves are falling gently to the ground. And here, wherever you are, you're part of this grand celestial choreography, this ancient rhythm that connects you to every living thing that has ever experienced the turning of the seasons. The next time you feel the first warm breeze of spring, or crunch through autumn leaves, or watch snowflakes fall in winter's hush, remember that you're experiencing something truly cosmic, a consequence of our planet's tilt, our moon's steadying influence, and our position in the solar system. You're feeling the effects of events that happened billions of years ago, yet continue to shape every day of your life. In this way, the changing seasons are perhaps our most intimate connection to the vast story of the universe itself. The biological world around you operates on countless invisible schedules, each one carefully tuned to Earth's steady 24-hour rhythm. Your morning coffee tastes better because your circadian clock has primed your metabolism for caffeine. The flowers in your garden open their petals precisely when pollinators are most active. Even the bacteria in your gut follow tidal patterns of activity that mirror the rise and fall of ancient seas. All of this intricate biological choreography depends on one simple fact: Earth keeps spinning at a predictable pace. But what happens when that fundamental rhythm suddenly stops? If Earth's rotation ceased tomorrow, the first casualties wouldn't be buildings or cars, they would be living things. And the devastation would begin not with dramatic explosions, but with something far more subtle and insidious: the complete breakdown of biological time itself. Every organism on Earth, from the tiniest microbe to the largest whale, has evolved internal clocks that synchronize with our planet's rotation. These aren't just convenient adaptations, they're essential survival mechanisms. When those clocks are suddenly thrown into chaos, life itself begins to unravel. Let's start with something close to home: your own body. Right now, as you listen to this, thousands of cellular processes are following circadian rhythms that have been fine-tuned over millions of years of evolution. Your core body temperature naturally drops in the evening, preparing you for sleep. Your liver produces different enzymes at different times of day to process nutrients most efficiently. Your immune system ramps up and down in cycles, fighting infections most aggressively when you're awake and focusing on repair while you sleep. Even your DNA repair mechanisms follow a 24-hour schedule, fixing cellular damage according to a biological timetable that assumes tomorrow will arrive in roughly 16 hours. When Earth stops spinning and plunges half the planet into permanent darkness while baking the other half in endless sunlight, these internal clocks don't just malfunction, they become completely meaningless. Your brain would continue producing melatonin and cortisol in their usual patterns for a while, but without the regular cycle of light and dark to reset these rhythms, your entire endocrine system would gradually drift into chaos. Sleep would become erratic, then impossible. Your metabolism would falter as your liver tried to process nutrients according to a schedule that no longer exists. Your immune system, confused by the lack of day-night cues, would either become hyperactive, attacking your own tissues, or shut down entirely, leaving you vulnerable to every pathogen in your environment. But human biology represents just one thread in the vast tapestry of life that would begin unraveling. Consider the plants around you, those quiet green organisms that seem so passive and unchanging. In reality, they're incredibly sophisticated timekeepers. Most flowers open and close their petals on precise schedules, timing their displays to coincide with the activity patterns of their pollinators. Sunflowers don't just track the sun's movement across the sky, they anticipate it, turning eastward before dawn in preparation for sunrise. Many trees time their leafing, flowering, and fruit production not just to seasonal changes, but to daily light patterns that help them coordinate with the insects, birds, and mammals they depend on for reproduction. In a world where half the planet bakes in permanent sunlight, while the other half freezes in endless night, these delicate timing mechanisms would collapse entirely. Plants on the day side would initially attempt to continue their normal cycles, opening their stomata to collect carbon dioxide and photosynthesize. But without the cooling respite of night, they would quickly begin to overheat. Their cellular machinery, evolved to function within narrow temperature ranges, would start to break down. Proteins would denature, cell walls would rupture, and photosynthesis itself would grind to a halt as the chlorophyll molecules that capture sunlight began to bleach and degrade under the relentless solar radiation. On the night side, the story would be equally grim, but opposite in nature. Plants would initially continue photosynthesizing using their stored energy reserves, but without sunlight to replenish these stores, they would begin a slow process of starvation. The cold would compound their problems as cellular fluids began to freeze, rupturing cell walls and destroying the delicate structures that make life possible. Within weeks, possibly days, most plant life on both sides of the planet would begin to die. The collapse of plant life would trigger a cascading ecological catastrophe that would make the immediate physical destruction from Earth stopping seem almost trivial by comparison. Plants form the foundation of virtually every food web on the planet. They convert sunlight into chemical energy that feeds everything from tiny soil bacteria to massive herbivores. When the plants die, everything that depends on them follows in a predictable sequence of ecological collapse. Herbivorous insects would be among the first to go. These creatures often have incredibly specialized relationships with particular plants, timing their life cycles to coincide with specific flowering or leafing patterns. Many butterflies, for example, emerge from their pupae precisely when their host plants are producing the nectar they need to survive. In a world where these plants are either burning under constant sunlight or freezing in perpetual darkness, these intricate relationships would shatter instantly. The insects would emerge to find their food sources dead or dying, and would themselves perish within days. The death of herbivorous insects would doom the countless species that depend on them for food. Insectivorous birds, many of which time their migrations and breeding cycles to coincide with peak insect abundance, would find themselves in a world suddenly empty of their primary food source. Bats, which hunt flying insects using echolocation, perfectly adapted to predict their prey's behavior patterns, would find that those patterns no longer exist. Spiders, whose webs are positioned and timed to catch insects following predictable daily movement patterns, would find their hunting strategies useless in a world where such patterns have ceased to exist. But the ecological collapse wouldn't stop with the obvious predator-prey relationships. Some of the most devastating impacts would come from the breakdown of mutualistic relationships, those partnerships between species that benefit both participants. The relationship between flowering plants and their pollinators represents one of the most important of these partnerships. Bees, butterflies, hummingbirds, and countless other pollinators have evolved to visit flowers at specific times of day when nectar production is highest and when the conditions are optimal for both plant and pollinator. These visits transfer pollen between flowers, enabling plants to reproduce while providing pollinators with the energy they need to survive. In a world of permanent day and night, these relationships would dissolve instantly. Flowers that normally open at dawn to attract morning pollinators would find themselves either baking in endless heat or frozen in perpetual cold. Day-flying butterflies would be unable to navigate in the permanent darkness of the night side, while nocturnal pollinators, like many moths and bats, would be overwhelmed by the constant blazing sunlight of the day side. Even if some pollinators managed to survive the initial catastrophe, they would find that the flowers they depend on are no longer producing nectar on any predictable schedule, if they're producing it at all. The breakdown of pollination would doom most flowering plants to extinction within a single generation. Without pollinators to transfer genetic material between individuals, most plants would be unable to reproduce sexually. While some plants can reproduce asexually through runners, bulbs, or other vegetative means, these methods don't provide the genetic diversity that species need to adapt to changing conditions. In a world undergoing the most dramatic environmental change in Earth's history, this lack of genetic flexibility would be a death sentence. Aquatic ecosystems would face their own unique catastrophes. Many marine organisms, from tiny plankton to massive whales, follow daily vertical migration patterns, rising toward the surface at night, to feed and diving deeper during the day to avoid predators and harsh sunlight. This daily migration is one of the largest movements of biomass on the planet, involving billions of tons of living organisms following a rhythm that has persisted for hundreds of millions of years. When Earth stops spinning, these migration patterns would become instantly obsolete. Plankton that rise to feed on surface nutrients under cover of darkness would find themselves trapped in either permanent blazing sunlight or endless frigid darkness. The tiny copepods and krill that form the foundation of marine food webs would lose their ability to track optimal feeding conditions, leading to massive die-offs that would propagate up through every level of marine ecosystems. Fish that rely on daily feeding patterns would find their prey distribution completely altered. Many species time their spawning to daily and seasonal light cycles, releasing eggs and sperm when conditions are optimal for their offspring's survival. Coral reefs, already stressed by warming oceans, would face the additional challenge of losing the daily light cycles that their symbiotic algae depend on for photosynthesis. On the day side, corals would bleach and die from excessive heat and light. On the night side, they would slowly starve as their algal partners shut down production in the absence of sunlight. Even the deep ocean, seemingly isolated from surface conditions, would eventually feel the impact. Many deep-sea creatures depend on the constant rain of organic matter that drifts down from surface waters. This marine snow consists largely of dead plankton and other organisms from the productive surface layers. When surface productivity collapses due to the breakdown of daily migration patterns and the death of photosynthetic organisms, the deep ocean would gradually be starved of this essential food source. The impact on large animals would be both immediate and delayed. Migratory species would face perhaps the greatest challenges. Many birds navigate using the sun's position, following routes that depend on predictable daily and seasonal changes in solar angle and intensity. In a world where the sun never moves from its position in the sky, these navigation systems would become useless. Birds attempting to migrate would find themselves flying in circles or heading in completely wrong directions, unable to reach their traditional breeding or feeding grounds. Large herbivores, like elephants, zebras, and wildebeest, which follow seasonal migration routes timed to grass growth and water availability, would find that these patterns no longer exist. The grasslands they depend on would either burn under constant sunlight or freeze under perpetual darkness. Even if some grass survived in the narrow twilight zone between day and night, it would be insufficient to support the massive herds that currently roam places like the Serengeti or the Great Plains. Predators would face a double catastrophe. Not only would their prey species be dying from habitat loss and food scarcity, but their own hunting strategies would become obsolete. Many predators are precisely adapted to hunt at specific times of day. Lions do most of their hunting during the cooler hours around dawn and dusk. Owls hunt at night, using hearing and vision adapted to low-light conditions. Hawks and eagles soar on thermals that form predictably as the sun heats the ground during the day. In a world of permanent day and night, these hunting strategies would no longer work, and these magnificent predators would join their prey in extinction. Perhaps most tragically, the species that might seem best equipped to survive, those with the most sophisticated behavioural flexibility, would often be the most vulnerable. Many of the most intelligent animals, from dolphins to primates to elephants, have complex social structures and learned behaviours that are passed down through generations. These cultural adaptations are often precisely tuned to environmental rhythms that would no longer exist. A mother elephant's knowledge of where to find water during the dry season becomes useless when there are no more seasons. A dolphin pod's coordinated hunting techniques become ineffective when the fish they target no longer follow predictable daily movement patterns. The psychological stress on surviving animals would be immense. Many species have been shown to suffer from depression and anxiety when their environmental rhythms are disrupted even slightly. Captive animals in zoos often develop behavioural problems when their lighting schedules are irregular. In a world where all environmental rhythms have ceased to exist, the psychological toll on surviving animals would likely be devastating, reducing their ability to reproduce, care for their young, or even maintain basic survival behaviours. Even the smallest organisms wouldn't escape the biological catastrophe. Soil bacteria and fungi, which play crucial roles in nutrient cycling and plant growth, follow daily activity patterns that would be completely disrupted. Many of these microorganisms are sensitive to temperature fluctuations and depend on the daily heating and cooling cycle to regulate their metabolic processes. On the day side, soil temperatures would quickly rise beyond the tolerance of most soil life. On the night side, freezing temperatures would kill or severely damage these communities. The death of soil microorganisms would have cascading effects that would persist long after any potential recovery. These organisms are responsible for breaking down organic matter and making nutrients available to plants. Without them, dead plant and animal material would accumulate without decomposing, while simultaneously the nutrients that new plants would need to grow would remain locked up in forms they cannot use. This would create a devastating feedback loop, where the capacity for life to recover would be progressively diminished. Yet perhaps the most sobering aspect of this biological catastrophe is how quickly it would unfold. While the physical effects of Earth stopping its rotation would be immediately apparent, the biological effects would cascade through ecosystems in a matter of days or weeks. Unlike gradual environmental changes that allow some species to adapt or migrate to more suitable habitats, the sudden cessation of Earth's rotation would happen faster than any biological adaptation could possibly occur. Some organisms might survive in small refugia, tiny pockets where conditions happen to remain tolerable. Perhaps some hardy bacteria around deep-sea volcanic vents, which already live in extreme conditions and don't depend on surface productivity, might persist. Maybe some insects or small mammals could survive in underground burrows in the twilight zone between permanent day and night. But these would be tiny remnants of Earth's once magnificent biosphere. The silence that would gradually fall over the Earth would be profound and heartbreaking. No more dawn chorus of birds greeting the sunrise, no more evening symphony of crickets and frogs. No more seasonal migrations filling the sky with wings and the roads with hoofprints. No more flowers opening to greet pollinators. No more bees humming through meadows. No more whales singing in the deep ocean. The biological clock that's been ticking for billions of years, that has given rhythm and meaning to life on Earth, would simply stop. This is perhaps the most tragic aspect of Earth's rotation ceasing. It wouldn't just kill individual organisms or even individual species. It would break the very mechanisms that make complex life possible. The intricate timing systems that coordinate ecosystems, the daily rhythms that synchronize reproduction and feeding and migration, the seasonal patterns that have shaped evolution for hundreds of millions of years. All of this would simply cease to exist. And yet, in contemplating this biological apocalypse, we gain a deeper appreciation for the delicate miracle that is life on our spinning planet. Every sunrise that resets 1 trillion circadian clocks, every season that triggers migration and reproduction, every tide that brings nutrients to coastal ecosystems, all of these depend on our planet's steady, reliable rotation. The biological clock of Earth doesn't just mark time, it creates the very conditions that make time meaningful for living things. As you listen to this, your own biological clock is quietly ticking away, synchronized with the rotation of the planet beneath your feet. Your heart beats in rhythm with circadian cycles that connect you to every other living thing on Earth. You are part of an ancient biological symphony that has been playing for billions of years, and will continue playing for billions more, as long as our planet keeps spinning through the cosmic dark. The cessation of Earth's rotation would thus unravel the very fabric of timekeeping and biological order. Calendars, clocks, and the simple markers of age, birthdays, anniversaries, seasons, would lose all meaning. Humanity's shared rituals, from the daily cup of coffee at sunrise to the global celebration of New Year's Eve, would vanish along with the spinning planet. Yet even in this frozen, bifurcated world, life might cling to the margins. Underground habitats, deep ocean trenches, or domed cities in the twilight belt could offer refuge from unending glare or unyielding darkness. Engineers and visionaries would race to develop artificial day-night lighting, thermal regulation, and closed-loop ecosystems. Our species' greatest test would be to recreate the rhythms we once took for granted. In the next installment, we'll examine how Earth's magnetic field, spun into being by the planet's rotation, would falter without its churning core, exposing the surface to lethal cosmic radiation. We'll explore the fate of our atmosphere once the Coriolis effect dies away, and how the oceans would settle into new static basins. Join us as we delve deeper into the profound consequences of a world that has come to a standstill. Part 6. The collapse of Earth's magnetic field and catastrophic weather. We've watched the immediate chaos unfold as everything loose gets flung eastward at tremendous speeds. We've seen the massive redistribution of water as our planet's bulge collapses. But there's something else happening in this catastrophic scenario. Something invisible, yet equally devastating, that would unfold over time. If Earth suddenly stopped spinning, we would lose one of our most crucial protective shields, our magnetic field. This isn't just another inconvenience to add to our growing list of problems. The collapse of Earth's magnetic field would fundamentally alter the conditions for life on our planet in ways that are both subtle and terrifying. To understand why this matters so much, we need to first understand what our magnetic field actually does and how Earth's rotation creates it in the first place. Deep beneath our feet, about 2,900 kilometers down, lies Earth's outer core. This isn't the solid iron ball at the very center of our planet, but rather a churning sea of liquid iron and nickel, heated to temperatures exceeding 4,000 degrees Celsius. This molten metal doesn't just sit there quietly, it's in constant motion, flowing and swirling in complex patterns that scientists are still working to fully understand. Now here's where Earth's rotation becomes absolutely crucial. As our planet spins, it creates what's called the Coriolis effect throughout the entire Earth, including in this liquid outer core. The rotation causes the flowing liquid metal to twist and spiral in specific ways, creating electrical currents as the conductive ion moves through existing magnetic fields. These electrical currents, in turn, generate more magnetic fields which influence the flow of the liquid metal, which creates more currents and so on. It's a self-sustaining system that scientists call the geodynamo. Think of it like a massive, planet-sized dynamo, the same principle that generates electricity in a bicycle dynamo when you pedal, but on an almost incomprehensible scale. The faster the rotation, the stronger the effect. The steadier the rotation, the more stable the magnetic field. For over 4 billion years, this system has been working reliably, creating a magnetic field that extends far out into space, forming what we call the magnetosphere. This magnetosphere is invisible to us, but its effects are profound. It acts as a cosmic shield, deflecting most of the charged particles that stream toward us from the sun in what's called the solar wind. Without this protection, these high-energy particles would slam directly into our atmosphere and surface. The magnetic field also protects us from cosmic rays, high-energy particles from deep space that can be incredibly damaging to living tissue. But if Earth suddenly stopped spinning, this entire system would begin to break down. The complex patterns of flow in the outer core that depend on the Coriolis effect would be disrupted. The geodynamo would start to weaken, and our magnetic field would begin to fade. Now, this wouldn't happen instantly. The magnetic field wouldn't just switch off like a light bulb the moment Earth stopped rotating. The liquid ion in the outer core has tremendous inertia, and it would continue moving for some time, even after the planet's surface stopped. But without the organizing influence of rotation, these flows would become chaotic and eventually die down. Scientists estimate that if Earth's rotation completely stopped, we might lose most of our magnetic field within a few thousand to tens of thousands of years. In geological terms, that's remarkably fast. In human terms, it might seem like we'd have time to adapt, but the weakening would begin immediately, and even a partially weakened magnetic field would have serious consequences. As our magnetic shield weakened, more and more charged particles from the solar wind would penetrate into our atmosphere. These particles would interact with gases in our upper atmosphere, stripping away molecules and gradually eroding the atmosphere itself. We can see this process in action on Mars, which lost its magnetic field billions of years ago and has since had most of its atmosphere stripped away by the solar wind. The loss of atmospheric protection would be gradual but relentless. Our ozone layer, which protects us from harmful ultraviolet radiation, would be particularly vulnerable. High-energy particles from space would break apart ozone molecules faster than they could be naturally replenished. As the ozone layer thinned, more UV radiation would reach the surface, causing increased rates of skin cancer, cataracts, and genetic damage in all living things. But the effects wouldn't stop there. The weakening magnetic field would also mean that more cosmic radiation would reach Earth's surface. These high-energy particles can damage DNA, disrupt cellular processes, and make large areas of the planet uninhabitable for complex life. The increased radiation would be particularly dangerous for any technology we rely on. Satellites would be bombarded with particles that could damage their electronics. Power grids could be disrupted by geomagnetic storms that would become more and more severe as our protective field weakened. Even more dramatically, the changing magnetic field would completely alter one of Earth's most beautiful natural phenomena, the aurora borealis and aurora australis. These dancing lights in the polar skies are created when charged particles from the solar wind interact with our magnetic field and atmosphere. As the field weakened and became irregular, auroras might appear at unexpected latitudes, sometimes reaching much farther toward the equator than ever before. While this might be beautiful to observe, it would also be a visible sign of our planet's weakening defences. The collapse of the magnetic field would also have profound effects on weather patterns, though these would be more subtle and would develop over longer timescales. Our magnetic field influences the behaviour of charged particles in the upper atmosphere, which in turn affects atmospheric circulation patterns. Changes to these patterns could alter jet streams, storm tracks, and seasonal weather cycles in ways that are difficult to predict but potentially devastating for agriculture and ecosystems. Navigation systems that rely on magnetic compasses would become unreliable as the magnetic field weakened and its poles shifted unpredictably. Animals that use magnetic navigation, including many birds, sea turtles, and marine mammals, would find themselves disoriented and unable to complete their traditional migration routes. This would have cascading effects throughout ecosystems as these animals failed to reach breeding grounds or feeding areas. Perhaps most concerning of all would be the gradual transformation of Earth's atmosphere itself. Without the magnetic field to deflect the solar wind, our planet would slowly begin to resemble Mars. The constant bombardment of charged particles would strip away our atmosphere molecule by molecule. The process might take millions of years, but it would be inexorable. The thinner atmosphere would be less able to retain heat, leading to dramatic temperature swings between day and night. Weather patterns would become increasingly erratic as the atmosphere lost its ability to distribute heat effectively around the planet. Eventually, the atmosphere might become so thin that liquid water could no longer exist on the surface, except in the deepest valleys and at the lowest elevations. All of this represents a fundamental shift in the habitability of our planet. While the immediate effects of Earth's rotation stopping would be catastrophic and visible, the loss of the magnetic field would represent a slower but equally devastating transformation. It would change Earth from a world teeming with life to one that could barely support it. In this scenario, any survivors of the initial catastrophe would find themselves living on a planet that was slowly becoming more and more hostile to life. The very air they breathed would be gradually stripped away. The radiation levels would steadily increase. The weather would become more and more unpredictable and extreme. It's worth noting that this process might not be entirely uniform or predictable. As the magnetic field weakened, it might not simply fade away smoothly. Instead, it could become chaotic, with the magnetic poles wandering unpredictably around the planet or even temporarily reversing. During these periods of magnetic instability, some regions might be better protected than others, creating pockets of relative safety in a world becoming increasingly hostile to life. The collapse of Earth's magnetic field represents one of the most profound long-term consequences of our planet's rotation stopping. While the immediate effects would grab all the attention, this slower catastrophe would ultimately determine whether Earth could continue to support complex life at all. It's a reminder that our planet's rotation isn't just about day and night, or even about the movement of oceans and atmosphere. It's about the fundamental forces that make Earth habitable in the first place. In our hypothetical scenario where Earth's rotation has ceased, this represents perhaps the most chilling aspect of all. Even if humanity somehow survived the initial chaos, even if we found ways to adapt to the new climate and geography, we would still be living on borrowed time. Our planet would be slowly dying, losing the invisible shield that has protected life for billions of years. The magnetic field that we never see, never feel, and rarely think about would quietly fade away, taking with it our planet's ability to sustain the rich, complex biosphere that we call home. Now that we understand how galaxies collide and merge, reshaping the cosmic landscape through gravitational encounters that stretch across millions of years, we come to another profound force that has shaped the universe: the mysterious substances that remain largely invisible to us, yet control the very architecture of cosmic structure. When we look out into space, we see a universe filled with stars, galaxies, and glowing gas clouds. But here's something that might surprise you as you drift towards sleep. Everything we can see, every sparkling star and swirling galaxy, represents less than 5% of what's actually out there. The remaining 95% of the universe consists of two enigmatic components that don't emit light, don't reflect it, and barely interact with ordinary matter at all. We call them dark matter and dark energy, and together they represent one of the deepest mysteries in modern science. Dark matter makes up about 27% of the universe. It's called dark not because it's sinister or foreboding, but simply because it doesn't shine. It doesn't absorb light, emit light, or scatter light. It's invisible to our telescopes, yet its gravitational effects are written across the cosmos like invisible ink revealed only through careful observation. Without dark matter, galaxies as we know them simply couldn't exist. They would have never formed in the first place, and if they had somehow managed to assemble, they would have flung themselves apart long ago. The evidence for dark matter first emerged in the 1970s when astronomer Vera Rubin was studying how far stars orbit within galaxies. She expected to find that stars farther from the galactic centre would move more slowly, just as the outer planets in our solar system orbit more slowly than the inner ones. But that's not what she discovered. Instead, she found that stars throughout spiral galaxies were moving far too fast for the amount of visible matter present. According to the laws of gravity, these rapid moving stars should have been flung out into intergalactic space like sparks from a spinning firework. The only explanation that made sense was that there had to be much more matter in these galaxies than what we could see. This invisible matter, this dark matter, was providing the extra gravitational pull needed to hold the galaxies together. It was like discovering that an iceberg extends far below the waterline, except in this case the hidden portion was 5 times larger than the visible part. As astronomers continued their investigations, they found dark matter's fingerprints everywhere. When they studied colliding galaxy clusters, they observed something remarkable. The visible matter, primarily hot gas, would collide and slow down during these cosmic crashes, but the dark matter would pass right through, continuing on its trajectory as if the collision had barely affected it. This behaviour provided compelling evidence that dark matter interacts gravitationally but not electromagnetically, confirming that it truly is a different type of substance entirely. Computer simulations of cosmic structure formation painted an even clearer picture. When scientists tried to model how galaxies and galaxy clusters formed over cosmic time, they found that ordinary matter alone couldn't do the job. The universe needed dark matter's gravitational scaffolding to build the intricate web of filaments and nodes that we observe today. Dark matter provided the framework upon which ordinary matter could gather and eventually form stars and galaxies. But what exactly is dark matter made of? This question has puzzled scientists for decades, and the answer remains elusive. We know what it isn't. It's not made of ordinary atoms, the building blocks of stars, planets, and people. It's not black holes, brown dwarfs, or any other form of ordinary matter that simply happens to be dark. It appears to be something entirely new, a type of particle that was created in the early universe, but barely interacts with the matter we're familiar with. Several candidates have been proposed. One possibility is that dark matter consists of weakly interacting massive particles, or WIMPs, hypothetical particles, that would have the right properties to explain dark matter's behaviour. Another candidate is the axion, an extremely light particle that would have been produced in vast quantities after the Big Bang. There are even more exotic possibilities, including sterile neutrinos and particles that exist in hidden dimensions. Despite decades of searching, dark matter particles have never been directly detected in laboratory experiments. Scientists have built incredibly sensitive detectors deep underground, shielded from cosmic radiation and other interference, hoping to catch a dark matter particle as it occasionally bumps into ordinary matter. So far, these experiments have come up empty-handed, adding to the mystery of this invisible component of our universe. While dark matter is puzzling, it's dark energy that truly challenges our understanding of reality. Making up about 68% of the universe, dark energy is even more mysterious than dark matter. Its existence was discovered almost by accident in the late 1990s, when two teams of astronomers were studying distant supernovas to measure how the expansion of the universe was slowing down over time. The assumption was that the universe's expansion, which began with the Big Bang, should be gradually decelerating due to the gravitational pull of all the matter it contains. Just as a ball thrown upwards slows down due to Earth's gravity, the universe's expansion should be slowing down due to the collective gravity of all the matter and dark matter within it. But when the astronomers analysed their supernova data, they discovered something shocking. The universe's expansion wasn't slowing down at all. Instead, it was speeding up. Galaxies were moving away from each other at an accelerating rate, as if some mysterious force was pushing them apart. This discovery was so unexpected and revolutionary that it earned the 2011 Nobel Prize in Physics for the scientist involved. This accelerating expansion could only be explained by the presence of a new form of energy that permeates all of space and pushes outward against gravity. Scientists named it dark energy, though like dark matter, the dark simply refers to our ignorance about its true nature. Unlike dark matter, which clumps together and helps build cosmic structure, dark energy appears to be smoothly distributed throughout space, exerting a constant outward pressure that grows stronger as the universe expands. The implications of dark energy are profound and somewhat unsettling. As the universe continues to expand and accelerate, galaxies that aren't gravitationally bound to our local group will eventually move so far away that their light will no longer be able to reach us. In the far distant future, observers in our galaxy might look out into space and see only the handful of galaxies in our immediate cosmic neighbourhood, with the rest of the universe having receded beyond the horizon of visibility. But we're not there yet. For now, dark energy and dark matter continue their invisible dance, shaping the evolution of the cosmos in ways we're only beginning to understand. Dark matter provides the gravitational glue that holds cosmic structure together, while dark energy pushes everything apart on the larger scales. Together, they represent a cosmic tug-of-war between the forces of attraction and repulsion, with dark energy slowly but steadily winning. What makes this story even more intriguing is that these invisible components weren't always dominant. In the early universe, ordinary matter and radiation held sway. Dark matter began to take control during the formation of the first stars and galaxies, providing the gravitational framework for cosmic structure. Dark energy, meanwhile, only became dominant relatively recently in cosmic history, when the universe had expanded enough that its outward push could overcome the inward pull of matter and dark matter combined. This cosmic evolution means that we're living during a unique period in the universe's history. We can still see distant galaxies and study the cosmic web of structure that dark matter has helped create. We can observe the afterglow of the Big Bang and trace the universe's history from its earliest moments. Future civilizations, billions of years from now, won't have access to many of these cosmic signposts. They'll inhabit a universe that appears much emptier and more isolated than the one we observe today. The search for understanding dark matter and dark energy continues with increasingly sophisticated experiments and observations. New telescopes are mapping the distribution of matter in the universe with unprecedented precision, looking for the subtle ways that dark matter's gravity bends and distorts light from distant galaxies. Particle accelerators are creating conditions similar to those just after the Big Bang, hoping to produce dark matter particles in the laboratory. Underground detectors continue their patient vigil, waiting for the telltale signature of a dark matter particle interaction. Meanwhile, theoretical physicists are exploring radical new ideas about the nature of space, time, and reality itself. Some propose that dark energy might be a property of empty space itself, a quantum field that fills the vacuum with energy. Others suggest that our understanding of gravity might be incomplete, and that what we attribute to dark matter and dark energy might actually be signs that Einstein's theory of general relativity needs modification on cosmic scales. As you settle into sleep tonight, consider this remarkable fact. You are made of the rare stuff, the 5% of the universe that shines and interacts and forms complex structures like planets and people. You are a temporary arrangement of atoms that were forged in the hearts of ancient stars, organized by forces we understand, surrounded by a vast ocean of mystery that we're only beginning to explore. The invisible universe of dark matter and dark energy reminds us that reality is far stranger and more wonderful than our everyday experience suggests. What we can see and touch and measure directly is just the tip of the cosmic iceberg. The rest remains hidden, waiting to be discovered, a testament to the profound mysteries that still surround us. In the grand story of the cosmos, we find ourselves as conscious observers made of stardust, trying to understand a universe that is mostly invisible to us. It's a humbling thought, but also an inspiring one. We may represent just a tiny fraction of what's out there, but we're the fraction that can wonder, that can question, that can seek to understand the magnificent darkness that shapes our cosmic home. So as the night settles around you and your thoughts begin to drift, remember that you're surrounded by invisible forces and mysterious energies that stretch across billions of light years. Dark matter flows through you and around you, its particles perhaps passing through your body millions of times each second without leaving a trace. Dark energy gently pushes at the very fabric of space, ensuring that the universe continues its ancient expansion into an uncertain future. Sweet dreams, fellow traveller, through this mysterious cosmos. You carry within you the atoms of ancient stars, and you rest within an invisible universe that continues to unfold its secrets, one discovery at a time. Looking at the content of this Earth's rotation stoppage scenario, I need to continue building on the established narrative about biological impacts, technological consequences, and the broader implications for life on Earth. Based on the summary, I should focus on the technological and societal collapse that would follow such a catastrophic event. The sudden halt of Earth's rotation would trigger a cascade of technological failures that would fundamentally alter human civilization. Our modern world relies on an intricate web of satellite-based systems, all carefully calibrated to Earth's predictable 24-hour rotation cycle. GPS satellites, which form the backbone of global navigation and timing systems, would find themselves completely out of position. These satellites are programmed to maintain precise orbital patterns that assume Earth's continued rotation, and without this movement, their positioning algorithms would become meaningless within hours. The implications extend far beyond simple navigation errors. Every smartphone, every autonomous vehicle, every precision farming system, and every financial trading platform depends on GPS timing signals for synchronization. Modern electrical grids use GPS timestamps to coordinate power distribution across vast networks. When these timing signals fail, the cascading effects would be swift and devastating. Power grids would struggle to maintain stability without precise coordination between generating stations. Financial markets, which execute millions of transactions per second based on GPS-synchronized timestamps, would face chaos as trading algorithms lose their temporal reference points. Telecommunications networks would suffer massive disruptions. Cell towers rely on GPS for network synchronization, and without it, calls would drop, data would fail to transmit, and emergency services would lose their ability to coordinate responses. The internet itself, which depends on precisely timed data packet routing, would experience widespread failures as servers across the globe lose synchronization. Aviation would face an immediate crisis. Commercial aircraft rely on GPS not just for navigation, but for precision approaches to airports, collision avoidance systems, and flight management computers. With GPS systems failing and traditional navigation beacons overwhelmed by the atmospheric chaos, air traffic control would be forced to ground flights worldwide. Ships at sea would find themselves navigating by stars and compass alone, assuming the magnetic chaos from Earth's disrupted magnetic field hadn't rendered compasses useless as well. The collapse of our technological infrastructure would compound the physical disasters already unleashing across the planet. Emergency responders would be unable to coordinate rescue efforts as communication systems failed. Weather monitoring satellites, no longer able to maintain their positions relative to Earth's surface, would lose their ability to track the massive storm systems brewing in the disrupted atmosphere. Early warning systems for the approaching tsunamis and earthquakes would fall silent just when humanity needed them most. But perhaps most unsettling would be the failure of systems we rarely think about but depend on absolutely. Water treatment plants use GPS timing for automated chemical dosing systems. Without precise timing, these systems would shut down as safety protocols engaged, leaving populations without clean water just as natural freshwater sources were being contaminated by the oceanic redistributions. Food distribution networks, which rely on GPS for logistics coordination, would collapse as supply chains broke down. Nuclear power plants present a particularly sobering scenario. These facilities use GPS for precise timing of safety systems and grid synchronization. While they're designed with multiple backup systems, the combination of GPS failure, grid instability, and potential seismic activity from the rotation stoppage could trigger emergency shutdowns worldwide. Even in shutdown mode, these plants would require careful monitoring and cooling, tasks made exponentially more difficult without reliable communication and transportation systems. The human cost would be immeasurable. Hospitals would lose access to GPS-timed medical equipment, from precision surgical robots to synchronized life support systems. Patients being transported by ambulance would be stranded as navigation systems failed and communication with hospitals was lost. Emergency services, already overwhelmed by the physical disasters, would find themselves operating blind and deaf, unable to coordinate responses or even locate people in need. In the longer term, assuming any pockets of humanity survived the initial catastrophe, the technological dark age that followed would be unlike anything in human history. Unlike past civilizations that collapsed gradually, this would be an instantaneous return to pre-electronic survival. The survivors would possess all the theoretical knowledge of our technological civilization, but none of the functioning infrastructure to apply it. Rebuilding would face unique challenges. Our modern technology assumes certain stable conditions: predictable day-night cycles, stable magnetic fields, and consistent atmospheric conditions. In the post-rotation world, with its 6-month days, chaotic magnetic field, and extreme weather patterns, the very foundations of our technology would need to be reimagined. Solar panels designed for Earth's current light cycles would be useless. Electronic devices would need hardening against the increased radiation. Even basic agriculture would require completely new approaches adapted to the extreme day-night cycle. The psychological impact on survivors would be profound. Humans have evolved with circadian rhythms tied to Earth's rotation. Without the familiar cycle of day and night, sleep patterns would be severely disrupted. Mental health crises would be inevitable as people struggled to adapt to the alien environment their home planet had become. The loss of familiar skies, no more sunrise and sunset as we know them, would remove one of humanity's most basic shared experiences. Yet in this darkest of scenarios, human ingenuity might still find ways to adapt. Underground settlements might provide protection from the surface chaos while maintaining more controlled environments. Geothermal energy could replace solar and wind power in the new atmospheric conditions. Small communities might develop new social structures adapted to the extreme day-night cycles, perhaps hibernating during the long night periods and maximizing activity during the extended days. The Earth itself would continue its journey through space, still orbiting the Sun, still a blue planet when viewed from afar. But it would be an Earth transformed beyond recognition, a world where the very concept of a day would need redefinition, where north and south would lose their magnetic meaning, and where the survivors would look up at an alien sky, forever changed by the simple absence of something that had been so fundamental to existence that no one had ever truly imagined its loss. In the end, the cessation of Earth's rotation would represent not just a physical catastrophe, but a complete break with the rhythms that have defined life on our planet for billions of years. It would be the ultimate reminder of how much we depend on the quiet, invisible forces that keep our world turning, literally and figuratively, and how quickly everything we take for granted could change forever. And so, as we reach the end of our journey through the extraordinary and the ordinary, we arrive at a world forever changed by the sudden stillness of our spinning planet. The silence that would follow Earth's abrupt halt would not be the peaceful quiet of a sleeping world, but the profound hush of a system fundamentally broken. Throughout our exploration, we've witnessed the cascading effects of this cosmic catastrophe. We've seen how the immediate violence would give way to longer-term devastation, how the loss of our magnetic shield would strip away the very atmosphere that cradles life, and how the delicate rhythms that govern everything from ocean currents to biological cycles would shatter like glass. But perhaps the most sobering realization is how utterly dependent we are on forces we rarely consider. The rotation of our planet, spinning faithfully for over 4 billion years, is not just a cosmic curiosity, it's the invisible foundation upon which all terrestrial life has evolved and thrived. From the circulation patterns that distribute the heat around the globe, to the Coriolis effect that shapes our weather systems, from the centrifugal force that helps maintain our planet's shape to the day-night cycle that regulates the biology of virtually every living thing, Earth's rotation is woven into the very fabric of existence. In contemplating this impossible scenario, we gain a deeper appreciation for the elegant stability of our world. The 24-hour day that structures our lives, the predictable rising and setting of the sun, the seasonal migrations of animals, the ebb and flow of tides, all of these depend on our planet's steady spin. Even our sense of direction, our understanding of time, and our technological systems from GPS satellites to power grids rely on Earth's rotational constancy. The gradual changes we've discussed, the slow lengthening of days, the moon's gentle retreat, the shifting of magnetic poles, these remind us that our planet is not static but dynamically evolving. Yet these changes occur on timescales so vast that they're imperceptible within human lifetimes, allowing the complex systems of life to adapt and flourish. As we drift toward the end of this exploration, perhaps there's comfort in knowing that Earth's rotation is one of the most stable and enduring features of our cosmic neighbourhood. The same physics that would make a sudden stop so catastrophic also ensures that such an event is virtually impossible. Our planet will continue its ancient dance, spinning through space with the same steady rhythm that has sustained life for eons. So tonight, as you settle into rest, take a moment to appreciate the quiet miracle happening all around you. Feel the solid ground beneath you, carried along at over 1,000 miles per hour through space. Notice how the sun sets and the stars wheel overhead, following patterns as old as civilization itself. Listen to the wind, shaped by forces born of our planet's spin, and watch the clouds drift across the sky in their eternal circulation. In a universe of chaos and change, Earth's rotation remains our constant companion, invisible, faithful, and absolutely essential. It asks nothing of us, yet gives us everything. Our days and nights, our seasons and weather, our very existence on this spinning sphere we call home. The Earth turns as it always has, as it always will, carrying us all forward through time and space. And in that turning lies not just the story of what would happen if it stopped, but the deeper truth of why it never will. We are passengers on a cosmic carousel that has never missed a beat, and likely never will. Rest easy, fellow travellers. The world keeps spinning just as it should, just as